Hello and welcome back to the optimization method class. This is the second course after the midterm exam. Today we're going to talk about separable programming. So if you recall, in the previous topic we talked about quadratic programming. These two problems are different, quadratic and separable. However, the basic idea to solve these two problems are very similar. So the idea is the original problem is nonlinear programming. We have the objective function or the constraints are nonlinear. Then we do something such that everything becomes linear. And then once that everything becomes linear, we have a linear programming. And then we may solve that linear programming using simplex algorithm. Specifically for quadratic programming, we use the phase one of the two-phase simplex method. And then here in the separable programming, you will see that we do the same thing, same idea. We try to convert everything that is nonlinear to become linear, and then we solve that linear programming problem using the simplex algorithm. So let's start. So what is a separable programming problem? It is a nonlinear programming problem which has this kind of form. So in the objective function, you see that you may separate the function into the sum of the terms that involves one variable only. So you can separate the objective function into the terms that only involves x1, only involves x2, only involves x3, and so on. Same thing happened with the constraint. You may separate the constraint, you may separate the equation in all constraints as the sum of the terms that only involves xj. So you can say that this part only contains x1, this part only contains x2, this part only contains x3, and so on. So you really can separate the equations. So if you have that kind of nonlinear programming problem, then it is called a separable programming problem. So as I've said before, this separable programming may be solved by converting the nonlinearity into all linear things. So the idea here is that we are going to approximate the function which is originally nonlinear by several piecewise linear function. So let's say you have a function that looks like that, which is nonlinear. We are going to approximate it using several piecewise linear function. Okay, so now everything is linear. You may have a linear programming problem, and then we may use simplex algorithm to solve it. Now let's see an example of a nonlinear programming problem, which later we may see that it is a separable programming. Okay, so in this example, oil must determine how many barrels of oil to extract during each of the next 2 years. So the oils that is extracted in the first year can be sold for $30 minus X1. The oil that is extracted in year 2 may be sold by this price, $35 minus X2. And then the cost of extracting oil in year 1 is X1 squared. The cost of extracting oil in year 2 is 2 times x2 squared. And then 20 million barrels of oils are available, and then at most 250 million can be spent on extraction. So you know that we have two constraints here. The first is that the amount of oil is only $20 million. And then for the money, we also have the constraint of $250 million that can be spent for extraction. Now, what we need to decide is how much oil we are going to extract in year 1 and year 2. So That is our decision variables. Let's say x1 is the millions of barrels of oil extracted during year 1, and x2 is the amount of oil that we extract during year 2. Now, if we formulate that problem, we see that this is a non-linear programming problem, okay? And then we can see that the objective is to maximize the profit. So this is what we get from selling the oil minus the cost of the first year and the second year to extract the oil. And then we have two constraints. The first is the amount of oil that is available here, and then the other one is the money for doing extraction. Okay, so this is our non-linear programming problem. But then if you notice that you actually may separate the objective function and constraints based on the variable. For example, you notice that these two, they only involves x1. Similar thing in the constraint, you see that this only involves x1, this also only involves x1, and the remaining only involves x2. So that's why this is a separable programming problem, because both in the objective function and the constraints, you may totally separate the terms that, okay, this only contains x1, that only contains x2. To linearize a function, we need to determine the upper bound and lower bound for each variable xj to make sure that our variable will always fall into this range. So in our example, we may set the lower bound equals 0 because we see that x1 and x2 must be greater than or equals to 0. So the lower bound is 0. So a1 is the lower bound for x1 and a2 is the lower bound for x2. Now what about the upper bounds? So for the upper bounds, you may take a look at this constraint and then see that because the sum of x1, x2 must be less than or equals to 20, you can say that, so the lower bound for, the upper bound for x1 and the upper bound of x2 is 20. In other words, x1 and x2 may not exceed 20. Well, this upper bound is not super tight. It means that if you take a look at the first constraint, you may get the lower bound, you may get the upper bound that is lower than 20. But in this case, it is okay if your bounds is not very tight, because later when you solve the problem, you still have these two constraints. So it's okay if your bound is a bit greater than the allowable range of the decision variable. What is not okay is that if your bounds cuts away or deletes some of the range of the allowable values for the decision variable. So for example, if you set the upper bound, let's say equals 8, it's not okay because you cut away a lot of x1 and x2 values that are still allowable. So for example, I think if x1 equals 10, it's still allowable, right? Because 10 squared is still 100, and then 10 is still less than or equals to 20. So the point is you should set the upper bound and lower bound such that you do not cut away some values that is actually allowable for your decision variables. Now that we have defined the upper bound and lower bound as the range of the allowable values for our decision variable, we are going to cut that range into some grids. Okay, so we are going to determine the grid points. So here in this example, aj is the lower bound of your variable j, and then bj is the upper bound for your variable xj. So this is the entire allowable range. Now we are going to cut this range into k grids. So you're going to cut, and this is the final cut. You notice that the first grid point is equals to the lower bound, and then the last grid point is equal to the upper bound. So here we divide the entire range into k grids. Okay, and then the point where the cut is made is called the grid point. So pj1 is the first grid point for variable j. pj2 is the second grid point for the variable j, up to pjk is the kth grid point of variable j. So going back to our example, for example, we say that we're going to cut the range from 0 to 20 by doing this cutting from 0 to 5, and then 5 to 10, and then 10 to 15, and then the final one is 15 to 20. Okay, so here we do the same grid points for both x1 and x2. So you are allowed to create different grid points for x1 and x2, but in this example, we use the same grid points for x1 and x2. And also, they happen to have the same lower bound and upper bounds. So the bounds are the same and the grid points are the same. Although, as I've said before, you may have different bounds and different grid points for each variable. Okay, so now you see that we have divided the range of the variable xj, which ranges from 0 to 20, into 1, 2, 3, into 4 grids. 1 grid, 2 grid, 3 grid, and 4 grids. And then the grid points are 0, 5, 10, 15, and 20. If you have two grid points that are next to each other, for example, PJR, so this is the rth grid points, and then PJR plus 1, so the next grid point, you may define any point between them using this linear combination formula. So any point between these two grid points may be defined as the multiplication of the first grid point with the coefficient delta plus the second grid point with the coefficient 1 minus delta. And then delta must be between 0 and 1, including 0 and including 1. So here's the illustration. Because we're just talking the point, I'm going to cover the function first. Okay, so this linear combination says that if you have two grid points next to each other, any point between them, xj here, may be defined as xj equals delta times this plus 1 minus delta times this point. Okay, now here's a question. We have seen the linear combination formula in the previous slide. Now let's say the grid points are 10 and 15, and then the points between them, xj, equals 12. What is the value of delta such that you may define 12 using the grid point 10 and the grid point 15? I will pause the video to give you the time to think about the answer, and then I will give you the answer after the pause. So the answer is delta equals 3 over 5, because if you plug in this coefficient, 3 over 5 times 10 plus 2 over 5 times 15, because 1 minus delta is 2 over 5, you will get the result 12. So you will see from this example that we may define any point between the grid points using the linear combination of the grid points. Now, we have seen that we may define the point between two grid points. The same idea will be used to define the function value between these 2 points. So This is the function value of PJR. This is the function value of PJR plus 1. Now the idea is, instead of looking at the original function, which is nonlinear, now we just assume that everything between these 2 points is linear and then get this value using the linear combination idea. So it's the same idea with what we've seen before, defining a point using the linear combination of two adjacent grid points. Here is the same when we want to define the value, the function value of a point. We just take the linear combination of the function value of the two adjacent grid points. So here's the example. So suppose again 10 is our PJR and then 15 is our PJR plus 1. And then we look at the function value of 10 is here, the function value of 15 is here. And then to get the function value at 12, we are not going to look at the actual function anymore. We are going to take this linear line between the function value of 10 and 15, and then we take the linear combination such that we get the function value for 12, which is equals 60. There is a chance that this approximation is different with the actual function value, of course, because the original function is nonlinear, and here we are taking the assumption that everything is linear between two grid points. So of course there will be a difference between the actual function and the approximation. You may also notice that the difference will be smaller and smaller and smaller if your grid points is very close to each other. For example, instead of 10 and 15, if your grid points is 10 and 11, the difference will be smaller between the approximation and the actual function. And then if your grid points is even smaller, the range, for example, 10 is your first grid point and then your second grid point is 10.001, of course the approximation is even closer to the original function. Okay, so this is how we formally write down that we are going to approximate the variable, the objective function, and the constraints based on the grid points. So first, for the variable, we write down in the constraint part that our xj is a linear combination of the grid points. Grid point 1, grid point 2, up to grid point k, and then there is a coefficient delta j1, delta j2, up to delta jk. Remember that the sum of all delta must equal 1, and then each delta must be greater than or equals to 0. So this is how we define our decision variable as the linear combination of the grid points. We do the same thing for the objective function and the constraint. So for the objective function, which is originally is the function of xj, now we say that the objective function is the function of grid point 1, function of grid point 2, function of grid point k, and then put the coefficient same as before. Similarly, for the constraint, previously the constraint is a function of xj. Now it becomes the function of grid point 1, function of grid point 2, function of grid point k, but don't forget to multiply each of them with the corresponding coefficient. Now, the last thing that we need to guarantee to make the solution works well for the problem is that we need an adjacency assumption. Adjacency assumption means that we need to activate two grid points that are next to each other. We don't want to activate two grid points that are very far from one another because the solution will be very bad. So this is an illustration of what I meant. if we have, let's say the point is 12, as we've seen before, we would like to activate the grid point at 10 and the grid point at 15. Because if we activate the grid point at 0 and the grid point at 20, then the approximation for the point 12, the function value will be very far, right? Because you use 2 points that is very far from 12 to approximate the function value at the point 12. You want to use the adjacent grid point such that your approximation will be as close as possible to the actual function. Now let's work on our example. In our example, we may separate the objective function into the function of x1 only and the function of x2 only. Okay, so we are going to talk about the objective function first. And we're going to approximate this function using the grid points that we have defined. So this is our grid point. For x1 and x2, the grid point is 0, 5, 10, 15, and 20. So previously, our function is defined with respect to x1. Now what we're going to do is that we're going to define the function f1 with respect to each of this grid point. So this is what we're going to do. We compute f1 at the point 0. We compute f1 at point 5. We compute f1 at point 10. We compute f1 at point 15. So let's see this, for example. So 15, plug in 15 into x1. 30 times 15, 450, minus 2 times 15 squared. So 15 squared is 225. 2 times that is 450. So f1 15 equals 0. Okay, so you just plug in each of the grid point value to the f1 function, and then you have the representation of the points. So f1 0 is 0, f1 5 is 100, f1 10 is 100, f1 15 is 0, and then f1 20 is minus 200. So this drawing is not drawn to scale, so you will see that this is not very accurate. So this is just an illustration of what we did by computing the f1 of each grid point, and then later we are going to take the linear function among those function values. Now do the same thing for f2, x2, because the grid point for x2 is also the same like x1, which are 0, 5, 10, 15, and 20. We are going to calculate this row, f2 0, f2 5, f2 10, f2 15, and f2 20. For example, let's try f2 10. So you plug in 10 into here and there. So 35 times 10, 350, and then 3 times 10 squared is 300. So 350 minus 300 equals 50. So that is why this value is 50. Okay. Now we convert the objective function. So we convert the function that is originally depends on x. Now we convert it such as now it depends on the grid points, right? So you just take the sum of everything here. So 0 plus 100 plus 100 plus 0 plus minus 200, and then multiply it with delta, the corresponding delta. Okay, so this is 0, so we don't write this down. And the next is 100, so this is 100 goes here. Delta 1, 2 means it is the delta for the variable x1 with respect to grid point 2. And this is 100 again, so it becomes here. Don't forget to times delta 1, 3 because this is for x1 for the third grid point. And then minus 200 goes here times delta 1, 5. And then do the same thing for the x2 variable. So we have 100 is this 100 times delta 2, 2, 50 times delta 2, 3, minus 150 times delta minus 150 times delta 2, 4, and minus 500 times delta 2, 5. So we have seen how we may transform the objective function, which was originally nonlinear, to become linear using the grid points. Now we do the same thing for the constraints. So we have two constraints here, and then we can see that both constraints may be separated. So the first constraint may be separated into the term that contains x1 only and the term that contains x2 only. Similarly, for the second constraint, we may separate it into the term that contains x1 only and x2 only. So now we plug in our grid points to each of this function. So for the first constraint, we have this one. For the first constraint with respect to x1, you plug in all the grid points to the function g11. So the function is x1 squared. So 0 squared is 0, 5 squared is 25, 10 squared is 100, and so on. And then this row is for the first constraint, but with respect to variable x2. So the equation is 2 times x2 squared. This is still 0. 2 times 5 squared is 50. 2 times 10 squared is 200, and so on. And then do the same thing for the second constraint. So this is the second constraint with respect to x1. This is the second constraint with respect to x2. And then you may see the equation here. Second constraint with respect to x1, second constraint with respect to x2. So now we may write down the original constraint into the form of the linear combination of the function value of the grid points. Don't forget to multiply it with the delta. Okay, so same as before, 0 times delta becomes 0, so we don't write anything here. And then this 25 times delta 1, 2, this 100 times delta 1, 3, 225 delta 1, 4. So delta 1, 4 means it's the coefficient for x1 and grid point 4. And then delta, if we go on and then let's say here we have 50. So here 50 times delta 2, 2 because this is for variable x2 with respect to the second grid point. So the index may be quite confusing, but remember that delta is always the first index. For example, delta 2, 3 means delta for x2 at grid point 3. So regardless of which constraint that we are talking about, whenever it is talking about the variable x2, grid point 3, the delta is always delta 2, 3. So we combine everything that we have written down before. You don't need to write down that xj equals the linear combination of the grid points anymore, because you can see that we do not have x anymore here, right? So this formulation simply means that we now ask the linear programming to find which delta to activate. So you have delta 1, 1 up to delta 1, 5, and then delta 2, 1 up to delta 2, 5. And then now we are going to ask the linear programming to find which delta to activate such that we may maximize the profit. But don't forget we have the adjacency assumption. But let's talk about activating delta. If we activate two adjacent delta, means that we activate two adjacent grid point. When we have two adjacent grid point, it means that the objective function between them is assumed to be linear. The constraint between them is assumed to be linear. So basically, you just solve one linear programming problem, right? So simply by defining which grid point to activate, you can say that now the problem is just try to select which linear programming problem to solve. So you just look at a pair of grid points and then select the one that will give you the maximum result, and then you just solve it. So that's the idea of separable programming. Now, because we have this adjacency assumption here, which we don't explicitly define in the constraints, what we may do is that when we apply or we run the simplex algorithm, we need to follow this following notes. First, if all delta jk equals 0, then any delta jk may enter the basis. But if suppose delta jk prime is positive, then only its neighbor may enter the basis. So either delta jk prime minus 1 or delta jk prime plus 1 may enter the basis. So if you recall in the simplex algorithm, we always, in each step, we try to select one variable as the entering variable. Now, what this point says is that if you already have delta jk prime is already positive or is already in the basic variable, you may only choose the delta jk prime minus 1 or delta jk prime plus 1. So you cannot choose the delta jk that is far away from what you have so far. The first point says if you don't have any delta jk, then you may just select any of them. But then if you already have two delta jk that are already positive, so it means you already have a pair of grid points like here, this one and that one is already selected, then no other grid points may enter the basis. So these three rules actually just try to say that if you don't have delta jk selected already, then you're free to do anything. If you already have one delta jk selected, then you must select the neighbor, either the previous one or the next one. And then the final point is that if you already have two delta jk selected as the basic variable, then you cannot select any delta jk anymore. So you may solve the separable programming problem formulation using simplex algorithm by keeping in mind that adjacency requirements, those 3 points in the previous slide. However, there are some special situations where the adjacency is always satisfied. In other words, when you have these situations, you don't really need to care about those 3 points because they are always satisfied. So these are the special situations. In a maximization case, if each of your fj, xj is concave, and then each of your gij, xj constraint is convex, then this is the special situation where adjacency always satisfied. For minimization, if all your fj, xj is convex, and then all your gij, xj is convex, then it is also included into this special situation. So that's the end of this separable programming topic. And then next week we are going to start a brand new topic, which is game theory. So see you in the next one, and Thank you. Hello and welcome back to the Optimization Method class. This is the second course after the midterm exam. Today we're going to talk about separable programming. So if you recall, in the previous topic we talked about quadratic programming. These two problems are different, quadratic and separable. However, the basic idea to solve these two problems are very similar. So the idea is the original problem is nonlinear programming. We have the objective function or the constraints are nonlinear. Then we do something such that everything becomes linear. And then once that everything becomes linear, we have a linear programming. And then we may solve that linear programming using simplex algorithm. Specifically for quadratic programming, we use the phase one of the two-phase simplex method. And then here in the separable programming, you will see that we do the same thing, same idea. We try to convert everything that is nonlinear to become linear, and then we solve that linear programming problem using the simplex algorithm. So let's start.